Good evening, everybody. Welcome to Festival Hall and the Reedville Fishermen's Museum lecture series. This is the last of our 4 lectures this season, and I would like to thank everybody here for supporting the lecture series and attending these. And we hope that you will do so next year also. We have a few good potential speakers for next year that we have in mind. And of course, if anybody has some ideas for future lectures, please do let me know. I welcome all ideas for lectures. Anyway, I'd like to introduce Lynton Land. Lynton has received his master's and bachelor's degrees from Johns Hopkins University in Maryland, and he continued and received his PhD at Lehigh University in Pennsylvania. Dr. Land has held a number of professorships of geological sciences at the University of Texas. And Lynton especially is interested in geochemistry and other topics. Lynton has a strong passion for educating all ages, including and about the Bay and our surrounds. And he has given numerous talks, and I'm sure some of you have already heard him speak before at various lectures. But without further ado, I'm going to have Lynton take over and talk about climate change and the Chesapeake Bay for now and the future.
I'd like to talk about climate change and Chesapeake Bay. Go ahead with the next one. Sea level is rising. It has been rising for the last 18,000 years. Air and water temperatures are increasing. They have increased over the last 18,000 years or so, but the rise is now increasing. Precipitation is more episodic. We're worried about seawater becoming more acid, and all these things are caused by greenhouse gases, especially carbon dioxide, which we're venting into the atmosphere by burning fossil fuels. Fossil fuels really have only been used for, not that very long, and really since the Industrial Revolution in the middle of last century, they have really ramped up. I added 2 things at the bottom there because they are metrics for Chesapeake Bay. First is seagrass beds. And the seagrass beds are not expanding. Chesapeake Bay was once an ecosystem dominated by seagrass beds and oyster reefs. And they're both gone. And we did it. Seagrasses are nurseries. They provide sanctuary for especially juvenile fish and crabs. They provide food. They retard erosion. The reason they're gone is they're grasses. They need sunlight. You know that grass doesn't grow very well under your trees. Grasses want sunlight. If the water is turbid, light can't penetrate. The grasses can't grow. Why is the water turbid? It's turbid mostly because of algae, single-celled algae that grow in the water because of all the fertilizer we're putting into the bay. That makes the water turbid, prevents light from penetrating, grasses die off. Where's the fertilizer coming from? Half of it is coming from inefficient agricultural fertilization. That is something we have known for half a century. There's no doubt about it. And the solution to the bay's problem is to fertilize more efficiently. And we can do it. It's just we're not doing it, like we're not doing so many things. The dead zone is the other metric for the health of the bay, and we'll talk about that. Until seagrass beds expand and the dead zone decreases in size, nobody can claim that we're making any progress in improving water quality in Chesapeake Bay. And it has not happened yet. So whether it happens in the future, I don't know. Go ahead. The place to start with climate change is with what we call the Keeling curve. Way back in the 60s or so, a young man wondered if all the carbon dioxide that was going up the smokestacks was accumulating in the atmosphere. And so he said, well, I'm going to measure carbon dioxide in the atmosphere. In those days, the analytics were not all that easy. And there was problems, and you know, science works these things out. But anyway, this is what he's found. And I'm going to come back right here in a few minutes, because that's about when I started teaching at the University of Texas. So when I started teaching, this is what we knew. We didn't know this. And what you see is an annual variation. This is in the northern hemisphere. So as summer wears on, plants grow and take CO2 out of the atmosphere. But then after the deciduous plants become dormant, then respiration returns that CO2 back up to the atmosphere. The scary thing about this curve is it's concave upward, which means that the CO2 rate of increase is increasing. It ought to be flattening out. It ought to be going down. So these are absolutely certain data. Don't get the idea that these kinds of data are in their laboratories. These things have been determined all over the world by multiple laboratories, by multiple techniques. And so this is the way it is. Now let's go back to 1970. So this is what I had to teach. And the question is, why is the carbon dioxide going up? Well, CO2 is going up smokestacks. Nobody can argue that. That's obvious. They're out your exhaust pipes of your cars. I mean, that's the way it is. Is it enough to cause to change the carbon dioxide content of the atmosphere? So one of the things people did was they tried to estimate how much fuel had been burned, coal and oil and gas, and how much CO2 had been. And the early calculations were very puzzling because they showed that more CO2 went up the smokestacks than you could find in the atmosphere. And that was very puzzling. Well, when scientists have a puzzle, they say, oh boy, well, I can research something. This is fun. And okay, the question has to be answered. So he was wondering what the role of greenhouse gases were in warming the Earth. It had been predicted 100 years previously, a century previously, that burning coal, at that time that's mostly what they burned, could increase the concentration of CO2 in Earth's atmosphere and warm the Earth. And the calculations that were made a century ago on paper now, we didn't have computers, right? I'm not even sure we had slide rules. I guess we did, but anyway, well, the calculation was made and it's dead on. The guy was right 100 years ago. Well, when I was teaching this, you know, what's the alternative? Well, there's a clear alternative. We're coming out of an ice age. There's no doubt about that. I mean, geologists had wandered around Pennsylvania and Illinois and Indiana and mapped landforms that were left behind by the glaciers. When the glaciers expand, they go move south, you know, they bulldoze up rock piles and they leave behind features that geologists had identified as being glacial, and the geologists had mapped them. And the geologists knew that there were 4 major glaciations, 4 major ice advances, and the last one was dated by carbon-14 at 18,000 years ago. So we're coming out of a glacial period. Well, other people said, well, if we know where the ice was, then we can calculate how much ice there was. And since the water for the ice had to come out of the ocean, there's no place else it could come from, that meant that ocean must have been lower. Sea level must have been lower during the glacial period. How much lower? You see, scientists are quantitative. I know that as soon as I tried to teach using numbers, I could just, the guys in the back would pull their caps down over their noses. And all, but people don't like numbers. Scientists love numbers. So the question was, with knowing how much ice there was, how much water did that take out of the ocean? How much lower was the ocean? And the answer is about 140 meters. And at the same time, marine geologists were scurrying about in their ships using all this nice new technology that the Navy had let them have, and they were finding shoreline features out on the continental shelf at 140 meters depth. So one of the things that you need to be sure you understand is that that everything that one scientist or a group of scientists proposes is being tested by some other group of scientists that is looking at things from a completely different perspective. That's how science works. We're curious. We're just trying to figure out how the world works. It's a very complicated world. So when one person finds something and proposes it, everybody else says, well, wait a minute, I'm going to check that. And that's the way it goes. So we knew we were coming out of a glacial age, and maybe that's an explanation for this. Another thing that we knew, and we know, is the greenhouse effect. You all know how it works. At one time in your life, you have left a vehicle in the sun with the windows up, and you come back, and it can be so hot in there, you can't put your hand on the steering wheel. I mean, you all know that. It works. The physics of how electromagnetic radiation interacts with matter is well known. We know what happens. Photons from the sun pass through the glass with relatively little effect. They're absorbed by the vehicle or the Earth. And what is harder for people to grasp is that the parts of the vehicle or the Earth emit heat back. It's called infrared radiation. It's longer wavelength, lower energy radiation. And that radiation does not go through the glass as easily. It does not go through carbon dioxide. It does not go through the atmosphere as easily. And therefore the car heats up, the Earth heats up. Now infrared radiation, you've all felt it if you put your hand in front of a fire. And for those of you who saw the videos from the helicopter showing the Boston Massacre bomber lying inside a boat, we can detect it. There's instruments that will detect it very accurately. But that's what happens. So the greenhouse effect works. There's no question about it. And so there are these two competing ideas. We're coming out of a glacial period. The Earth is warming. Okay, it's what we expect. Or we're putting all this carbon dioxide in the atmosphere, and the greenhouse effect is working. Well, of course, what's happened with time is this. And with time, when I suppose back here, half the scientists were split. Half said, well, it's just coming out of the glacial cycle. The other half said, wait a minute, I think there's human greenhouse effect going on here. Today, 98% say that the observations that we make about warming and sea level rise are caused by us. Now, they're superimposed on top of the natural cycle, but the big changes that we see are caused by us. Okay, sea level will continue to rise. It is rising. It has risen since 18,000 years ago. Now, this is a very important slide, and it's a little bit busy, but I want you to stick with me. There are three curves here, A, B, and C. They all look pretty much the same. I think you'll agree with that. They're measuring completely different things versus time. So it's almost 500,000 years of Earth history. I want to concentrate on curve B. And what is being measured here is something that may sound a little strange. It's the ratio of oxygen 18 to oxygen 16. Common oxygen has 8 neutrons and 8 protons, so it's 16. But uncommon oxygen has 2 more neutrons, so it has a mass of 18 instead of 16. A Nobel Prize winning physicist at the University of Chicago had predicted that when organisms lay down skeletons of calcium carbonate, now calcium carbonate CaCO3, there's oxygen in it, that the ratio of these two isotopes would be sensitive to temperature. In other words, you could take the calcium carbonate skeleton and determine the temperature. Well, people wanted to know it was fine to know that the last glaciation was 18,000 years ago, but people wanted to know more. What was it like further back in time? And so the marine geologist said, well, heck, all we have to do is take a core of sediment and separate out the little animals, they're foraminifera, and measure them, and we'll learn as we go back in time how the temperature has changed. And that's exactly what you're seeing here. So these are the measurements. They can be correlated with temperature because we can correlate in the laboratory. We start with today. We see that not much changes for 4,000 or 5,000 years, and then boom, There's the glacial period. Guess what? 18,000 years ago. You see, we've tested what the glacial geologists are telling us on deep sea cores, and we're getting the same answer. So let's go back in time. It gets warmer and warmer and warmer and warmer and warmer, and all of a sudden it gets really warm. In fact, it gets warmer than today, because this is higher than that. Can we test that? Yes. How many of you have been to the Florida Keys? No, when you drive toward Key West, you are driving on top of a fossil coral reef. And coral reefs don't live in the air, right? So, well, it was warmer then. And we can date that coral reef. Guess what? 125,000 years. Exact agreement with the deep sea curve. So you see, we're beginning to piece together the history of the Pleistocene, the history of the glacial, interglacial the glacial advances and the interglacial periods before them. You see that it's cyclic. The cycles are caused by the amount of heat that the Earth receives from the sun. And the critical place on the Earth is the northern hemisphere. And I'm going to come back to this, all right? The northern hemisphere is where it's at in determining what happens to the temperature of the Earth. So here's an interglacial glacier, interglacial glacial, interglacial glacial, the last interglacial, the last glacial, and here we are today. Well, this was, I don't know how many millions of measurements were made to determine it actually early in my career, and then I turned my mass spectrometers in other directions. But anyway, geologists were looking for other ways to test this. Is this right? Is this the variation of glaciations and interglaciations? And then they started taking ice cores. And of course, ice cores do the same thing. Snow accumulates every year and gets compacted into ice. And if you drill into it, you're going back in time. And the neat thing about ice is that there's all kinds of stuff in it, like pollen and aerosols, and there's all kinds of things you can study. And you can imagine that that's being studied. But one thing you can do is you can crush the ice and get the gas out. And that tells you what the atmosphere was like. And so there you are, carbon dioxide. There it is today, glacial period, interglacial, glacial, interglacial. See, we got a record of what the carbon dioxide was. It was always between about 200 and 300 parts per million. So if you don't come away with anything else tonight, come away with this picture in your mind of these cycles. 200. Where are we today? We're approaching 400 parts per million. You see, we are way outside the past. There's no question we're still in a glacial cycle, glacial interglacial cycle. There's no doubt about that. So 80,000 years from now, we're going to be out here. And I wouldn't want to live in Toronto because it's under a mile of ice. And so is Chicago and New York and Boston. I mean, it's going to happen. But I mean, 80,000, 100,000 years, who cares, right? But what about 500 years? That's about the width of this line. How is this glacial interglacial cycle going to change anything in 500 years? Probably not very much. But this amount of CO2 in the atmosphere can change things tremendously. One thing that will change in 500 years is that there's no more fossil fuel left. I'm a geologist, all right? You heard it from me. The oil will be gone in the lifetimes of children being born today. All the oil that we can extract, and we're getting better at it. But geologists aren't stupid. We know that some of the stuff that's hard to get out of the ground, it's only hard because it's expensive. And if the price of the oil goes up, then we can apply technology to get more out of the ground. So we take that into account. With children being born today or your age, there's no more liquid oil in the ground unless we choose to leave it there. Okay? But if we burn it the way we're burning it, it's gone. 2 generations, natural gas is gone. 4 or 5 generations, the coal is gone. So Mother Nature is going to have her way, folks. Fossil fuels are finite. They're running out. The price is going to go up. And the sooner we move to other sources of energy, the smarter we are for our children. So 18,000 years ago, here's the Capes, here's the edge of the continental shelf. Sea level is out at 160 meters below its present position, 140, something like that. Chesapeake Bay was a river that came down and went out off across the continental shelf. The archaeologists have found Indian middens out here. It would have been scary to be a Native American at that time. Sea level, when the glacial period ended, sea level was rising your height in your lifetime. Now think about that. Daddy, why are we moving west? In Iroquois or Algonquin or something or other, right? Well, we're going to get drowned if we don't, so west we go. Chesapeake Bay, of course, is weird. It goes almost due south, not quite, but pretty much. And the reason is that 35 million years ago, there was a meteorite impact right there that created a big hole, and that's what Chesapeake Bay flowed into. It doesn't have anything to do with global warming. It does have something to do with our artesian aquifers, but that's it. I'm going to divert with two slides from Chesapeake Bay for just a second. One is glaciers. Glaciers are melting. This has been observed from a long time ago, and there's some spectacular images now. People, mount cameras firmly, and they take pictures every week or so. I mean, they're just unbelievable. But we're coming out of an ice age. Why shouldn't glaciers be melting? No, it doesn't prove anything. The people who are studying this are now they're able to study it more with these remote cameras. Plus, they can measure the thickness of the ice accurately with ground penetrating radar and other things. What they're finding is that in many of these glaciers, the retreat is increasing. In other words, they're going away faster. Now you ask yourself, given the two competing hypotheses that we're coming out of an ice age or its greenhouse gas effects, which of those hypotheses best fits the observation that the glaciers are retreating faster with time? Well, whichever, you can choose whichever you want. The other thing that has happened and is happening is that the Earth's heat budget is really controlled with the northern hemisphere. We have an ocean at the North Pole. South Pole, we have a continent. We have a lot more land mass in the northern hemisphere than we do in the southern hemisphere. And what happens is that in the wintertime, in the Arctic Ocean, here's the North Pole, right? So Greenland, Canada, US, Russia. In the wintertime, with the ice covered, the ice freezes out of seawater, but salt doesn't go into the ice. So the salt stays behind in the water gets salty. So you've got salty, cold water, that's dense water, and that dense water flows between Iceland and Norway into the North Atlantic Ocean. And that is a tremendous mechanism for transporting Earth's heat around. Well, here's the ice in 2007. They're predicting that the Arctic will be ice-free this year. You see, it's not as cold. We're not making as much salty water, as much cold water. We're in fact changing the circulation of the oceans. And scientists are not yet clear what the consequences of that are going to be. People have said, well, the Gulf Stream is going to go away. I think that's maybe going too far. But there will be changes which will affect climate, rainfall, temperature distributions. We just don't know what they are. The other thing that's scary about this is that when the pole is covered with, or the Arctic Ocean is covered with ice, the sunlight is reflected back off the ice. When there's more water there, that sunlight is absorbed and heats up. So that's called a positive feedback. The warmer it gets, the less ice, the more heat the Earth picks up, the worse it gets. And most of the projections that you see of ice behavior are predicting that things are getting worse faster than we had predicted a decade ago. Go ahead. Sea level rise locally. Louisetta has a recording tide gauge that you can get online. You can see what it is right now. And the historical record is there. They predict the tide. So it's a NOAA website. This is what has happened. Jamestown the sea level has risen 5 feet since Jamestown was founded. And that's why archaeologists are out putting on scuba tanks, wandering around trying to figure out if there are artifacts and stuff out there that they've missed. And the national park people are scratching their heads saying, what the heck are we going to do with Jamestown? It's doomed. You want to see Jamestown from a kayak, right? It's going to be flooded. So something has to happen. The Smith Point jetties, how many people have been out through the Smith Point jetties? The Smith Point jetties, the sea level has risen a foot since they were installed. They are lower than their design height. They are being overtopped from the north. And the jetties have always been dredged using earmarks. And we're told that there are no more earmarks. So the jetties need to be heightened. They certainly are going to have to be dredged every 5, 6, 7 years. I don't know where the money's coming from. I hope the local government does. We don't know where sea level is going. The legislatures tell us it's going there. You can only extrapolate linearly based on data. You know, you can't say it's more. It could be a lot more. There are some scary things about sea level rise. One of them is that people who study glaciers are noticing they're seeing lakes form in the summertime on top of the ice. Beautiful things. They're blue, clear, and there was one group that was camped out beside this lake, and in the middle of the night they hear this tremendous roaring and cracking and huge noise, and they woke up and the lake's gone. And what happened was that the cracks in the ice had the glacier's moving, right? It's not stable, it's moving toward the water. The cracks opened up, the water drained out. Where does the water go? Well, it goes down to the bedrock. Can't go into the bedrock, and it forms a lubricant. And some people are afraid that what's going to happen is we're going to get one of these big ice sheets that's going to break loose. And you could raise sea level 6 inches in a year if that happens. Who knows? We don't know what's going to happen. You're going to see shoreline losses because of rising sea level. There's no argument about it. This is a lousy slide, but I put it on here for a purpose. VIMS has a series of folios that show you the shoreline throughout the county, in fact, throughout the state, from air photos. So this is not something that people made up. The whole country was shot in 1937. So there you see, this is tip of Coles Island. Smith Point is down here about a mile or so. And so that's what's happened since 1937. You can see use the houses for scale. This is hardly eroded at all. I suppose it's got ironshore in it. I've never been there to look, but this is a tremendous amount of erosion here. So if you want to see what's happened locally near you, these photographs can be viewed. They're available. Go ahead. Wetland loss certainly is going to occur as sea level rises. This is along the Potomac River. This wetland is doomed. Wetlands remove nutrients. They provide habitat and sanctuary. They provide food and erosion control. This field is also in trouble. First of all, the Bay Act says that you should only farm within 100 feet of the water. Now, I suppose these are 100-foot lots, so I suppose this is about 100 feet. So that means that all this area here ought to be in trees, according to the Bay Act, unless you have a nutrient management plan, and then you can go to 50 feet. But still, 50 feet would be about there. Unless you have an erosion control plan and a pest control plan. And then you can go to 25 feet. In other words, the Bay Act has been gutted. And this isn't even 25 feet. So that's illegal. But of course, it's not in the forest. But setting that aside, this field is doomed because as sea level rises, so does the groundwater table. Right? And if you don't have 2 or 3 feet of unsaturated zone between the land surface and the water table, it's not deep enough for crops to get their roots and grow. And I think you can already see that things aren't doing as well here and here. And I think that's because that you're getting not enough unsaturated zone. That's what happened to Dameron Marsh. That's why we have a nature preserve at Dameron Marsh. They could no longer farm it and make money. The water table came up, they couldn't grow crops very well. The occasional storm would blow salt water in, and it would take a couple years for rain to wash that salt water out. So these sorts of fields are doomed. And of course, what happens here is another issue. There's a man lives near me who told me that in 1933, we had a 1933 hurricane. He told me that that morning his mother asked him to go out and pick apples. And he went out and he started to pick apples, and the rain came down, and the wind started to blow, and he went inside, and the whole house shook. His house survived, our house survived. We don't live that far from him. And then it got calm. And then the wind started to blow from a different direction. The eye of the hurricane went through Ophelia. And he showed me where the water came up. He said it was right here, put his finger on it. And I went out a couple of days later with a hand level and measured it was 8 feet. So all of you who live on the water, in the next couple of days, I want you to go figure out where 8 feet is. And stand there with your feet 8 feet above sea level, and imagine that is it better over here? Imagine that that's where the water level is, and now put 100-knot winds, hurricane force winds on top of that. And what's going to happen? Go ahead. That's Sandy. So if you think it was bad in 1933 around here, you wait till the next one hits. Now, is it going to hit? Yes. Is it going to hit because of global warming? No. It's going to hit anyway. It's just it's going to be worse because of global warming, because it's likely to be more powerful, and certainly sea level will be higher. So we just simply have to be prepared. In a coastal area like this, temperatures are going to continue to rise. Go ahead. The global temperature, here's the hockey stick that people talk about. There's been a lot of complaints about this. They're measuring it in urban areas and it's too hot. It's interesting that in an urban area, okay, it's hotter than it is in a rural area, but the temperature rise is the same. Okay. So people have taken that into account, and there's no question that temperature is going up. The northern hemisphere is critical because it's what controls really circulation of the oceans and an awful lot of atmospheric circulation. So I don't have time to go into that. In Chesapeake Bay, here's the records. The VIMS Pier is at Gloucester Point. CBL Pier is University of Maryland in the Patuxent. I mean, there isn't any question about it. In the last half century or so, the temperature has gone up. Probably the largest effects of the temperature, there are going to be droughts, there are going to be more fires, but the largest effect is going to be biological. And it's very hard to predict exactly what they are. Maybe some of them are going to be good. I mean, people live in Georgia and South Carolina just fine. We're going to become more like Georgia and South Carolina. Maybe that's not all bad. But there are going to be changes. The fisheries biologists at VIMS tell us that when water temperature reaches 15 degrees, bay fishes begin to spawn and migrate. And so that the migration is now 3 weeks sooner than it was 40 years ago. One of the problems here is that the fish may be responding to temperature, but the fish also depend upon food. This is something that the birders worry about. If one of the triggers for migrations is temperature, but another one is day length, then you see those two things get out of sync. Because the day length is the day length, and the temperature is getting warmer faster. Is it all bad? Is it going to cause extinction? No. But it's going to cause changes. And well, if some of the insects or birds or so forth affect your crops, then that's something to worry about. People have thought about, well, what's likely in the bay? We're going to lose winter flounder. Well, okay, who fishes for winter flounder anyway? Rockfish, the problem here is infections, that the fisheries biologists tell us that infections are more common in warmer temperatures. And I had a fisheries biologist at VIMS tell me he has never opened a Chesapeake Bay fish that he hasn't seen some kind of infection in it. And well, you have infections in you too, and you're here, so maybe it's not all bad. Well, it's okay, sturgeon, or we don't care. Blue crabs, declining eelgrass, I'm going to come back to that. But somebody did an experiment recently where they grew blue crabs under higher carbon dioxide, more acid conditions, and the crabs grew big. And they thought, oh boy, that's neat, that's cool. And then they opened the crabs up and discovered they didn't have any meat in them. And furthermore, the crabs were pissed off because they put some oysters in, oysters that the crabs normally wouldn't eat, they just tore into them. So I'm not telling you that's going to happen, all right? That's just one study. But in biology, there's all sorts of things that are going to happen that are unanticipated. And so we'd better be prepared for that. The oyster, we're going to talk about in a minute. The diseases are more prevalent at higher temperatures. You say, oh, well, we're going to have shrimp. They have shrimp down in North Carolina. Let's have a shrimping industry. That's the last thing we need in Chesapeake Bay. Shrimping is done by trawling, and they trawl up everything and dump it on the deck. It's called bycatch. They pick the shrimp out, and half an hour later, after landing in the sun, everything else is overboard. So we don't need that. So there will be changes, and maybe some of them will be good, but there will be changes. The eelgrass, the story is not good. The eelgrass is now near its southern limit of its range. So, and we're trying to bring the eelgrass back. People are going out planting, and they're having a little bit of success planting eelgrass, but you're not going to have much success until you clear the water up. And you're not going to clear the water up until you fertilize more efficiently. And then that's period. There's no backing away from that. But if it's near its southern range already, then it does not bode well for improving the eelgrass populations in the bay. Precipitation will probably increase. This is the least robust of the scientific conclusions as to what is going to happen to precipitation and so forth. But if precipitation does increase in the form of heavy downpours, we're going to get more severe thunderstorms. This is a model. I'm not telling you that it's right. I'm very skeptical of models sometimes. I grew up when computers started out. I made models. I know the flaws. And they're wonderful. Computers are wonderful these days. They have their place, but they're not as good as what you can see with your eyes. So we're scheduled for more thunderstorms, and runoff and groundwater discharge will add more nutrients, more algal growth, more turbidity, more oxygen consumption, all bad for the bay. And there's good reason to believe that this idea of more energetic atmospheric events is correct. And it took me half an hour in an oceanography lecture to explain this to the students, but the Earth receives most of its heat in the tropics. And I think everybody can understand that. But just as it's hard for people to grasp the fact that the sunlight that comes into your vehicle is being back radiated as infrared radiation back into space, it's hard for people to grasp the idea that the amount of heat that comes into the Earth, which is absolutely prodigious, has to go back into space. The same amount of heat. It's got to be balanced. If it's not balanced, the temperature goes bananas and you start boiling the ocean away. I mean, this is a huge amount of heat. The Earth gets more heat in the tropics than it back radiates to space, but it back radiates more heat at high latitudes than it gets from the sun. And what does that mean? That means that heat must be moved from the tropics to higher latitudes. Or if we have a heat excess in the tropics, we have a heat deficit at high latitudes. And how does the heat get moved? By the fluids called the atmosphere and the ocean. So if you heat the Earth up, you're going to have more heat being transferred, and the atmosphere and the ocean are going to be more vigorous. So there's every reason to believe that that will work. And runoff, of course, we increase runoff by large events, and phosphorus goes along with sediment, and so we're going to cause more phosphorus pollution. Go ahead. Red tides are another thing that we would expect to increase. People really don't understand these things. They're mostly caused by an organism called dinoflagellate. Think of it as an algae, that's okay. Some of them are toxic to animals, some of them are toxic to humans. And VIMS is asking people, if you see colored water this year, go to their website and tell them what you're seeing. That they want to know more about this. They can't be everywhere. You can be their eyes, and they may even send somebody out to take samples. So this is something that we need to know more about. But the conventional wisdom is the warmer it gets, the worse it gets, and it's caused by too much nutrient in the water. Seawater is going to become more acidic. I don't want to go into chemistry, but basically carbon dioxide creates an acid, and that lowers the pH and makes the seawater more acid. About half the carbon that goes up the stacks, it goes into the atmosphere. About a third of it is dissolved in the ocean. And the other 6, we're not really sure what happens to it. It's probably a whole lot of things happen to a little bit here, a little bit there, a little bit there. And it's very hard to figure out where it all goes. And some people have jumped on that and said, well, you don't know where the CO2 goes. We know that half of it is in the atmosphere and a third of it's in the ocean. That's probably enough. We don't need to go much further than that. Okay. Calcium carbonate is more soluble in acid. Here's a bunch of organisms you're called coccolithophore. They're little tiny algae. They're food for zooplankton and little fish, and at the bottom of the food chain. Well, you can see what happens when you grow them at elevated CO2. They are not very happy campers. So if you upset things at the bottom of the food web, that's not good. Oysters, the West Coast oyster hatcheries have had trouble, and they worked it down to an understanding that it was because the water was more acid. Now they're in a different situation than we are. They're getting water that's coming up from deep water in the ocean, but it's the concept that the lower pH, the acidity, makes it harder for the larvae to calcify. It upsets larval growth. And we don't know whether that, or how many other organisms that affects. We just simply don't know. So this is one of these uncertain changes that we may just have to live with. Last year they had trouble in the local hatcheries. I'm not going to predict what's happening this year. I've got 2 million oysters larvae right now striking, and they're doing just great. So let's hope it stays that way for the rest of the summer. The dead zone will expand. The dead zone, the bay has always had a dead zone. What happens is that in the spring, as the water warms and as we get spring rains, a surface layer, usually down to about 30 feet, the water becomes sufficiently light that it doesn't mix in with the deep water. So you get a layer, you get a stratification here. It's like wax on top of a jelly jar. And this water in the shallow is being stirred up by the wind, and everything's cool, but down here it's out of contact with the atmosphere, and microbes respire the organic material, use up all the oxygen, and we now have a dead zone. And one of the scary things to me is that this just doesn't sit here. If the wind blows the right direction, this thing can actually slosh up in the shallow water. And I think that's one of the reasons that bottom fishing is not what it was 15 years ago, but then maybe it's because I'm a lousy fisherman. But anyway, the dead zone sets up every year, and it affects the whole ecosystem. There are a lot of organisms that live in the surface waters that in the daytime they would like to be down here because it's dark and nobody can see them to eat them. But they can't go down here because there's no oxygen. So it affects the whole ecosystem. Why will it get worse? Well, it'll get worse for 2 reasons. Go ahead. Temperature increases. Warm water dissolves less gas than cool water, so if the water warms, there's less oxygen dissolved in it. And microbial respiration is higher in warmer water. So here's the dead zone. Here we are, right? This is about the worst place for it. You can see it on your depth sounder. What you'll see is that down around 30 feet in July and August, something or other, you'll see some return. Down below about 30 feet, you won't see anything. There's nothing down there enough to return your sound. So, so you can actually see it. And the temperature increases, it's going to get worse. If we get more episodic rain, large rain events, they're going to add more nutrients. That means more algae to grow, more to die, more oxygen to use. But the fresh water increases the stratification. It makes the surface water light. It makes it harder to mix in. So don't expect the dead zone to get any better. And global warming is going to make it worse. This is the scariest thing to me. Science can't predict everything, folks. Not by a long shot. And we just don't know what's out there is going to bite us. And maybe it'll bite us hard, maybe it won't bite. Maybe there'll be some good things happen. But the consensus is there are going to be more bad things than good things. And I think for the Bay that is certainly true. Poor polar bears. Well, it's us, it's just what we're doing, so we have to take the consequences. All right, I'm finished. Glad to answer questions if I can. If somebody wants to know what you do about this, it's the political, like everything else in this country, it's political. And that means it's money, because that's what politics is. And how you change the mindset of the politicians is, I know we've got one here, so he should cover his ears, but I don't know. The climate change lobby that Dr. Haugen has formed a chapter here, to me, is a very sensible approach. That is to tax carbon. Unless you put a tax on things, people aren't going to pay attention to it, and then give the money back to the people. Don't let the politicians get their grubby hands on it. It's going to disappear. Give it back to the people. I would do the same thing with the Bay. If I were king, I would tax fertilizer. I wouldn't tax slow release fertilizer, controlled release fertilizer, because that's what people should be using. Right? Most of it goes in the crop, not in the environment. I would tax the bejesus out of sewage sludge because it causes so much pollution. And then I would take the money and I'd buy riparian buffers. I'd buy up land within 100 feet of the water, and for whatever the going price of land is, and grow trees there. So if I were king, that would be my solution, but I'm not king. So
what's the percentage of nutrients that come from farms as opposed to like suburbia and everybody fertilizing their grass so they can have a green
right.
field so they can cut it with their lawnmower?
Right. The question is what's the balance of nutrient pollution from farm fields as opposed to lawns? There are calculations for lawns, and the problem with lawns is that most lawns aren't fertilized. I've got 4 acres of lawn. I don't put the dogs on it, and so do the squirrels, but that's about it. A lawn close to the water is fertilized as heavily as a field close to the water. But as you ride around, ask yourself, how many acres do I see in corn and wheat, and how many lawns do I see next to the water?
Like all the lawns in Washington, D.C. or
Sure.
suburbia out there, right?
Right. Suburban lawns, there's no question about it. Of course, there's a no phosphorus law that has gone into effect now. But the numbers have always shown that about half the nutrient pollution is because of fertilization of corn, wheat, and in the case of soybeans, they don't put nitrogen on, but they do put phosphorus on. So it's mostly corn and wheat. And those numbers have been robust almost half a century now, and haven't changed. No.
I'm an accountant because of freshman chemistry. How, with respect to the dead zone, and you talk about oxygen dissolving. Help me out there. Water is H2O.
Yeah,
There's no,
right,
there's no O
right.
in the water at that level, or?
That's a good question, and it's because of the way scientists speak sloppily. But when we say oxygen, what we really should be saying is dissolved elemental oxygen, O2, as distinct from the oxygen atoms that are in the water, H2O. So we're really saying dissolved oxygen. If there's no dissolved oxygen, it'll have the same effect on marine life as if all the oxygen would disappear from this room. We would all be dead instantly, right? Same thing. We must have O2, oxygen gas. No, can't do that. It would be great, but I mean, we can do it in the laboratory, but it takes too much energy. Can't do it. Oh, it's dissolved oxygen gas that matters.
Just a second.
Is the question on the slow release fertilizer that it's not as efficient as the stuff that's like shooting a shotgun at it, where it all dissolves right away?
Well, ideally, a slow release fertilizer releases the nitrogen and phosphorus over time as the plant grows. The plant needs fertilizer as it grows. And what is conventionally done is either to pile the fertilizer on at the time of planting, or to go back and side dress, or don't put as much on when you plant, but then run the tractor back through the field once or twice and add more. Now obviously that costs in terms of fuel and soil compaction and time, and not many farmers do it. The controlled release fertilizers are things like Osmocote that you can buy in the store. They work. The problem is there's no demand for them, and therefore there's no incentive to manufacture
But
them.
why no demand? It looks like to me, if it's slow release, you might just make one run with a tractor instead of several with the quick release
Well,
stuff.
because right now they cost more.
But even allowing for the additional cost to do multiple runs with a tractor on the quick release stuff, it's still cheaper for the quick release.
I think it
probably sewage.
Yeah, I think if controlled release fertilizers were manufactured on an industrial scale, that they would become cheaper, and farmers would use them. I mean, remember, this is not just Chesapeake Bay. We got a dead zone in the Gulf of Mexico the size of the state of Delaware in the summertime. Oh yeah, well, it's huge. It's all over the world, and farmers have gotten so used to doing. And I'm not knocking farmers. They've got to make a living, and we got to eat. We got to find our way out of this, folks, and we got to do it with, with everybody working together. But what happened was, at the end of World War II, we had all this tremendous capacity to make nitrogen, to make ammonia. We were using it for munitions, but we didn't need munitions anymore. So we used it for cheap fertilizer. And farmers got used to that. Pile it on, increase your crop yield, increase your profit, but don't pay for the pollution. You see, the pollution is an externality. It's not cost accounted. And that's what farmers do today. So, we've got to find our way out of this. Pointing fingers is not the solution. To me, the solution is to phase in controlled release or timed release fertilizers.
Just a minute.
Do farmers have to fertilize every year?
Yes.
They do.
Yep.
What about the methane going up into the air, like from the ice?
Right. Methane is
Methane in the deep sea.
methane is a greenhouse gas. It comes from lots of natural sources, but of course, production of natural gas, we have leaks, and that's not good. All the cattle that we raise, people laugh about it. Scientists going out and studying how important farts are to making methane, but it's a source, just like termites are a source. And so all the cattle that we raise increases the amount of methane that goes in the atmosphere.
Isn't it worse than CO2?
isn't it?
Worse than CO2.
Oh, it's worse than carbon dioxide. Remember, when the methane goes into the atmosphere, it gets oxidized to carbon dioxide. So yeah, it's bad, but it's in much lower concentrations than carbon dioxide, and so carbon dioxide is thought to be a more important problem. But methane is, and there are other greenhouse gases as well, nitrous oxides, for example.
Just a minute.
With respect to your graph of the glaciation and the cycles, what caused the curve to come back down? Hopefully it wasn't all the organisms dying and stopping giving off CO2.
No. Let's see, I can hopefully get to that. Thanks. The cause of the temperature changes, trying to do this sideways. That's the one you want. The cause of the temperature changes is variations in the amount of heat the Earth gets from the sun with time. The Earth's orbit is sometimes more circular and sometimes more elliptical. The Earth is tilted. The other planets aren't tilted. There's an interesting story there. It's got nothing to do with global warming, but it's interesting. But anyway, tilt is what gives us our seasons. So the more tilted we are, the more seasonal we are. And the tilt axis doesn't go around the sun like that. It precesses. I can't twist my... All right, and these three things have cycles. 20, 30, 40,000, 50,000 years. At some point, they all add up. So the Earth gets a lot more heat. Well, that's the interglacial period. And sometimes they all kind of cancel out. And the Earth gets less heat. Those are the glacial period. It was discovered by a Russian by the name of Milankovitch. It was very controversial when it was first proposed, but I've never heard of an alternative that makes any sense.
You had the one slide that showed that CO2 is increasing as a concentration in the air. So there's a corresponding decrease in O2?
In O2?
Yes.
Yes. It's very small. Remember, the carbon dioxide makes up less than 1% of the atmosphere. Oxygen makes up 20%. And so it's only been relatively recently that we've had the technology to measure the difference between 20.01 and 20.02. But yes.
How much is the oxygen going down?
Well, in proportion to the CO2.
Is that something that in future years that the level of O2 would get to a point where it affects living beings?
No. There's never been an issue with global warming about atmospheric changes becoming lethal. That would be huge. That would be far beyond anything that has ever happened on Earth. And of course, the proof of that, thank you, the proof of that is that life has been around for a heck of a long time. So yeah, the oxygen does, that was a test, that was a good question. See, that's the kind of test that you make. You would expect that the two things would be in opposite directions, but until the technology evolves to allow you to make the measurements, you can't test the hypothesis.
Lynton, what can one person on this earth do to help?
Elect the right people.
Well, we haven't been able to do that for a long time. That's always going to be a problem, though.
Yes, it is.
I mean, what can Fred Overson do, or what can Cass Overson do besides elect the right people? What can we do in our daily lives that we can maybe cause a little bit of a positive effect?
Well, of course, there are lots of things that if everyone did them, it would have an effect. Using less energy, conserving, recycling, all those things help. If we can get society to do it, it'll help. But our problem is we're relying on fossil fuels. And until we wean ourselves from that and realize that we have to, it's not going to change. There are some scary scenarios that you can come up with. I mean, think of what just happened in Boston. You had a couple of angry young men. There are lots of countries in this planet where you've got a lot of angry young men. They're overpopulated, they're corrupt, they're poverty-stricken. The angry young men have no hope of jobs. But the things that start to affect them, like Bangladesh starts to get rice fields flooded and the mountain glaciers don't provide enough water for the population. Who's going to get blamed for that? The West. And those angry young men have access to the internet. And the longer we procrastinate, the more cause they're given to say, well, they knew it was happening. The more cause they're being given to say, well, they knew it was happening. They didn't do anything about it. But that's scary. All energy is nuclear. The sun is a controlled hydrogen explosion, right? It's just gravity keeps it from going boom. The Earth's heat is generated, what you see in volcanoes and things like that, is generated by radioactive decay, which is a nuclear process. But yeah, the sun, hydrocarbons, coal, are fossil plant material. So if we can learn to emulate how plants use that energy to make useful compounds, that seems to me to be an area that has great potential. And of course, people are trying to do that like heck. I think ultimately it's going to have to, it should come down to solar. It could easily go nuclear. Because, I mean, nuclear power is very out of favor, but it's become an awful lot safer. It's not without risk, but it may come to that.
This will be the last question.
When you say nuclear, though, you're talking about fusion.
Yes.
Right, and we don't know how to do that.
No, we don't know how to do fusion, no. And we may never know.
That's the ultimate, that's the best.
If we could do it, but I mean, who knows? You know, think ahead 50 years. 50 years ago, what were airplanes like? So that's why we got to educate people, and why we have to push to open new vistas, and society needs to make the proper choices how to use what we discover, right? Scientists are not going to stop discovering. I mean, we have too much fun. You know, it's this great discovery thing. Society has to decide what we should do and what we shouldn't do. We shouldn't clone humans. You know, there's things we should not do, even though we might be able to do it. And that's a societal choice that has to be made. Yeah, I think the sun is probably the safest and the best source of energy, but I suspect that we will see more turn toward nuclear fuels, especially breeder reactors. That I mean, the two major objections are, well, they make plutonium, and you can make bombs out of it. Well, who's going to steal our plutonium? Come on, that's why we have the military. And the other question is, what do you do with the waste? Well, see, the breeder reactor gets rid of it. Basically uses it up.
Well, Lynton, thank you very much for a very informative lecture. And I'm sure most of you are watching a little bit. And thank you again for coming out to our last lecture of this season. Thank you.